Great, here we are. So last video of Unit 4, the world building unit. So this was I think one of the more unintuitive, I guess, would be the word, units, in that it involves kind of upending the way that you think about perception, or at least the way I've always thought about perception. Perhaps if you're completely new to kind of perceptual neuroscience and that kind of thing, maybe it's not so surprising. But for me, it was always a little bit tricky. But this idea of the brain being this prediction machine, but actually once you get your head around it, it makes perfect sense, right? It makes perfect sense, and it's once it cements itself in your brain, it's part of your new knowledge that you've gained from taking this course. It's kind of wonderful, and it allows you to do so much. We will be using this idea, this predictive processing, as it's called, to actually understand psychedelics. So a lot of what psychedelics do and their effects can actually be explained in terms of this way of looking at perception. And of course, if we're going to understand psychedelics, it makes sense to use the most up-to-date and modern ways of thinking about the way perception works, because of course psychedelics, they change perception, they change your world model. So that was why I think it's important that you actually understand perception in this way, using this top-down predictive processing model. Okay, so we're just going to finish off. We'll just very, very briefly reiterate this predictive processing model, and then we'll look at the a little bit at the way this is kind of implemented in the brain, or at least within the cortical columns. Okay, anyway, so this is our predictive processing model. We can even give that its name now, predictive. Yeah, my scroll, which you're used to now, see if you can decode that. Predictive processing, right? So the high-level model predicts or sends predictions downwards to the medium level down to the lowest level. And the lowest level's job is to predict this pattern of sensory information. If it gets it correct, happy days, that information is suppressed, it's ignored, it's filtered out, choose your term. And if it is not correct, then we have to send up these error signals, which are generated up through the hierarchy so the model can be updated. Okay, great. Now let's have a look at kind of the wiring of this process. So this is our old way of looking at a cortical column. Ooh, what's going on? This is our column. And right at the very, very beginning, I told you that it had 6 layers, and we even numbered them. We can do that, 1 to 6. Yes, Roman numerals. And we're going to separate these out into 2 groups. So these deeper columns, so kind of from here, we call the deep layer, or the deep layers of the cortical column. Here, makes sense, right? Deep layer, this is the top of the cortex, this is the surface, the cortex. This is deep down, so this is deep. Yeah, it's actually only like a few millimeters, but anyway, deep enough. So these are the deep layers, and these upper layers are not called the shallow layers, but the superficial layers. It doesn't mean they're important, just this is an anatomical term, superficial, towards the surface. Why am I telling you this? Andrew, why are you telling me this? Because it's relevant to predictive processing. So this was our predictive processing diagram before. This is how we imagined it. But these kind of blue boxes don't really tell you that much. Of course, they represent cortical areas, the groups of columns, but the actual connectivity looks kind of like this. So from the side, here, this is kind of what it looks like. So here we can see what our column looks like, right? Of course, we're really talking about large numbers of columns, but we're just going to show one column in each case. So this is our high level. Let me clear this now. Actually, I made a mess of myself. Not of myself, a mess of the board. Okay, this is the high level, right? And this is the low level. So here we have our, what's these called? Remember? Yep, these. Yep, this is our superficial. Let's call them super, why not? And these are our deep. So it's the deep layers of the cortical columns that are responsible for generating these predictions and actually sending their predictions downwards. So these yellow arrows here is the cortical column connecting to another cortical column lower down in the hierarchy and sending that prediction basically. So of course, there are many cortical columns at each level, and they're all sending their information downwards, but we're just showing one in this case. So this highest level cortical column is sending a prediction downwards to the superficial layer of a cortical column in a lower area of the hierarchy, and then again this lower cortical column in the hierarchy sends a prediction down to the superficial layer of columns in the lowest end of the hierarchy, and then of course that's receiving sensory information. Now the prediction errors, if there are any generated, and of course there are always going to be prediction errors generated in a real world situation, the model is never absolutely perfect. The prediction errors are actually sent from through this kind of superficial layer, so from superficial layer to superficial layer, like this. So this is kind of the wiring, if you like, of this predictive processing model, where these deep layers are responsible for constructing the model and generating the predictions, whereas the superficial layer is kind of carrying the prediction error. So there's this kind of separation of function with the deep layers of the cortical columns, and thus really the deep layers of the cortex itself, 4, 5, 6, have a different role than the superficial layers. The reason I'm telling you this is because we will be referring back to these deep layers when we actually start to look at psychedelic drugs and the way that psychedelic drugs work, because psychedelic drugs tend to work within specific layers of the cortex, which is why I'm telling you now what the functional difference between these deep layers and these superficial layers. And the idea, and I'm repeating myself again because I want you to remember this, that the deep layer of the cortical columns, deep layers of the cortical columns are responsible particularly for generating the model and for generating these predictions. Okay, great. Okay, so to sum up, so now we understand how your model is constructed in a hierarchical manner, and we understand that it is a model that generates predictions and tests them against sensory information from moment to moment. Now, here's a question. So what happens when you go to sleep at night and you start dreaming? So we already talked about dreaming a little bit in a few videos ago, I think. And of course, as I told you then, when you're dreaming, when you're asleep, your brain is essentially disconnected from the environment. So we haven't spoke about the thalamus that much, but the thalamus is this kind of relay station. It's right in the center of your brain, about the size of a walnut. It kind of looks like that, and it's one of its roles anyway is like a relay station. So it receives information from the retina, for example, and then it passes it so it receives the information from the retina and then passes it to the visual cortex. So if you want to basically disconnect the brain from the environment, you can shut down parts of the thalamus, and that seems to happen when you sleep, particularly when you start dreaming. So the question is then is what's different about the dream world? We already said that your dream world is the same model that that your brain uses to construct the waking world, right? It's the same model. And this is why, and studies have looked, there is a fairly substantial literature actually that's looked at people's dreams and the content and structure of people's dreams and actually compared them to normal waking life. And there is something called the continuity hypothesis of dreaming, which basically says that dreaming is continuous with waking. In other words, dreaming is kind of just like waking. And that turns out to be the case. Yes, you can have very strange dreams, and people will say, I have really fucking weird dreams, man, and that kind of thing. And yes, you can have very strange dreams, but on the whole, for most people, your dream experience, your dream life, the world that you live in within dreaming is actually very, very similar to the waking world. And people have even looked at how long you spend talking on the telephone, or how much TV you watch in dreams, and compared that to waking life. Found that it's actually comparable. The proportion of time you spend watching TV in the dreams is similar to the proportion of time you spend watching it in real life. It's kind of interesting. So that makes sense, of course, because the dream world is the same model. It's built from the same model. But dreams are different, right? Dreams can become kind of weird. And they often seem very unstable, and the scene kind of shifts. One moment you're sat in the front garden, maybe on your sofa in the garden like you do, drinking beer, on a sunny day, and then suddenly you're in an aircraft flying to, I don't know, Acapulco. Yeah, Acapulco, man. Dangerous though, be careful in Acapulco. It's quite a reputation. Anyway, you can't go there at the moment because of the virus. Actually, it depends when you're watching this. Maybe you're watching this in the future. Sorry, I started rambling. Yes, so dreams, right? So dreams can become very unstable. They can shift scenes very rapidly. 1 second you're talking to your mother, and then suddenly your mother becomes your boss or something, and of course you don't notice that. It's another interesting aspect of dreaming. You don't notice the weirdness normally, unless you're trained to, right? And you kind of become a lucid dreamer, that kind of thing. But yeah, so dreaming is, overall, in its gross form, the dream world is the same as the waking world. And that makes sense, right? Because it's the same model. Now, we can actually think about this in terms of our new predictive processing model of perception, and kind of explain why dreams are kind of very similar or the same, but different. Why is there this instability and fluidity in dreaming that you don't get in the waking state normally? Whilst the dream world is built from the same model as the waking world, when you're awake, remember that whilst you're always living within this model constructed by your cortex, this model is always being tested against sensory information, right? The model is always accountable to sensory information. So it's always testing on a rolling basis. It's always testing its model by making these predictions, and that basically means that the model is stable. It allows the model to be a stable and coherent model of the environment, because it has to be. Because it has to keep those prediction errors down. However, when you're dreaming, your brain is disconnected essentially from the environment. Sensory information normally passes through the thalamus and is relayed then to the visual cortices. That process is shut down during dreaming. So whilst your dream world is constructed from the same model as the waking world, there is no model testing. There's no testing against any sensory information. So if the model does kind of shift and change and update, and the scene shifts, whatever, there's nothing to basically tell the brain, wait a minute, this model is not working. So basically the brain can move freely through its various models of the environment without having to deal with error signals from sensory information, basically. So that's kind of cool. Okay, so that is the end now of Unit 4. This has been I think, a little bit a tricky unit. For me, it's always been, as I said, it's conceptually quite difficult to understand, but we're there now, and we're going to use everything we've learned about model construction and world construction in this unit and the prior unit. Ultimately, when we look at the effects of psychedelic drugs. Because, of course, psychedelic drugs, they change your model, they change perception. So we're going to be using what we've learned in this unit to explain that, which is, of course, the point of this course, right? It's psychedelic neuroscience. So, yeah, we've got to get to the drug now. Where are the drugs? They're coming up soon. So, looking ahead to the next unit, we're going to change gear. Change gear? I don't know whether up or down, or... Are we changing gear? You can't move sideways, can you, in gears? Changing track, more like a train, right? We're changing track, that's it. Yeah. We're changing track. We're changing to kind of molecular track now. So we've been working for the last 2 units at a very kind of high level. In other words, we've been looking at global brain activity, how your overall model of reality is constructed, and ultimately we'll get to how that's changed by psychedelics. But to do that, to achieve that, to get there, we need to think about the way psychedelics work at the molecular level. So we need to know what the psychedelic drug is doing, what that molecule is doing when it enters the brain, and basically starts interacting with the brain. So we'll need to look at how drug molecules interact with receptors and the effects that has on neurons, and the effect it has on cortical columns, and then ultimately on the world model. So this, okay, so I will see you then for Unit 5. Wow. See you soon. Thank you. I'm kidding. However, if you do want to support the production of future courses, or you just want to leave a tip, then there are virtual tip boxes below. There's PayPal, Ko-fi, or Ko-fi, whatever it is, even a Bitcoin address if that is your thing. Minimally, please like and subscribe. It really helps me. And please follow me on Twitter and Instagram if you use them, Alien Insect. And I think that's about it. I hope you're enjoying the course. Thank you.